Okay, so now we will look at the eigenvectors based community detection. Okay, now we'll go to an example to understand this process. So, given a graph, you want to identify the communities in this graph is using the eigenvectors approach. So, what you need is to find the eigenvectors of the graph. So you know from the fundamental thing that for a graph of say 6 vertices in this case, you're going to have 6 eigenvalues, and for each eigenvalue you will have an eigenvector. Okay. Now previously we were using the adjacency matrix to generate the eigenvalues and eigenvectors. Now you could use that, or as I'll show you soon, you can also use the adjacency list to generate the eigenvalues and eigenvectors. So basically you can either use the adjacency matrix or the adjacency list to generate the eigenvalues and eigenvectors. You're going to get the same result in both cases. So let me show a video, or let me show an example of how to do this. So this is our file that I'm going to work with. So let me type the adjacency list as you see. So you can either leave a blank space or a tab, it doesn't matter, either case it will work. So 1, 2, 1, 3, then 2 has an edge with 3, 3 has an edge with 4, then 4 has an edge with 5, 4 has an edge with 6, 5 has an edge with 6. So make sure the cursor is in the last line and it's not in a blank line. Now you can save it to a text file. So now I'm going to run this. So I gave you guys the module 7 adjacency list EVC zip file, so unzip it. This is what you're going to see as a folder. Now run the EVC underscore adjacency list executable jar file. So then you can open the adjacency list file that we just saved. So I saved it as EVC something, right? So this is the output. So these are the eigenvalues, and for each eigenvalue you have the eigenvector. So the eigenvectors are printed starting from the largest eigenvalues. Okay, so for 2.4142 the entries are 0.35, 0.35, 0.5, 0.5, 0.35, 0.35. Now for the next largest eigenvalue, which is 1.7321, these are the eigen entries in the eigenvector and so on. Okay, so for each eigenvalue you're going to have an eigenvector. Now I think I might have said this before, the entries in the eigenvector correspond to the vertices out there. So the first entry in each of this eigenvector will correspond to vertex 1. The second entry in each of these eigenvectors will correspond to vertex 2. The third entry in each of these eigenvectors will correspond to vertex 3 and so on. Now if you see in this eigenvector corresponding to the largest eigenvalue, which we call as the principal eigenvalue, and this is also called the principal eigenvector, all the entries are going to be positive. And actually we know that this corresponds to the eigenvector centrality of these vertices. And we know also a fundamental property that the adjacency matrix is going to have all positive entries. Okay, so if the adjacency matrix has all positive entries, all the entries in the principal eigenvector are also going to be positive. Now in our case of community detection, all the entries in the principal eigenvector indicating positive indicates that according to this eigenvalue and this eigenvector, all vertices are considered to be in one community. So that's what we can infer from this first principal eigenvector and the corresponding principal eigenvalue. So if all the 6 vertices are in one community, let us go ahead and calculate the modularity score. So run your pairwise modularity program and determine all the pairwise modularity scores. Sum them up. The total modularity score is 0.47 if all the 6 vertices exist as one community. So now what we're going to do is use the subsequent eigenvectors and see can we partition this graph into more communities such that the total modularity score can be increased. So the second largest eigenvalue, which is on 1.7321, and the corresponding eigenvector is this. Now if you see in this eigenvector, some entries are negative, some entries are positive. So we will group together the vertices that have negative entries in this eigenvector and group separately the vertices that have positive entries in this eigenvector. So entries for vertices 1, 2 and 3 are negative. So we'll group them into one partition, and 4, 5, 6 are positive, so we'll group them into other partition. Okay. Now let us go ahead and find the moduli scores of these two partitions. So for 1, 2, 3, these are the pairs we have to consider: 1, 2, 1, 3 and 2, 3, and these are the pairwise moduli scores. Their sum is 1.85. For the partition 4, 5, 6, these are the pairs and these are the pairwise moduli scores, and their total moduli score is also 1.85. Again, this is just coincidence, it need not be the case. This is because in this case it is a symmetric graph. Alright, so the total moduli score is 1.85 plus 1.85, which is 3.7. So that means instead of having all the 6 vertices in one community and having a moduli score of 0.47, we could partition the graph actually to two communities like this and have moduli score of 3.7. So now we need to decide, do we need to partition these communities further? For example, do we need to partition 1, 2, 3 into 2 or more communities, similarly 4, 5, 6. So we could find out that using the third eigenvalue and the corresponding eigenvector. So the third largest eigenvalue is negative 0.4142, and the corresponding eigenvector is this. So now you see here, in the previous eigenvector we have the first 3 entries as negative, and now you see in this eigenvector the first and second are positive, the third is negative. That means if we were to partition 1, 2, 3 further, 1 and 2 should be together, 3 should be separate. So that's what this eigenvector indicates. Similarly, 4, 5, 6 had positive entry in the second eigenvector. Now here 4 is negative, 5 and 6 have positive entries. So that means if we were to partition 4, 5, 6, 4 should be as by itself in one community, and 5 and 6 are together as another community. So this is what we're going to end up with. Okay. Now if you now compute the moduli scores of this partitioning, for 3 the moduli score is 0, for 1, 2 the moduli score is going to be less than 1. So totally the moduli score of this partition is going to be less than 1, because less than 1 plus something 0 is also less than 1. Whereas we got for 1, 2, 3 is 1.85. So if we were to partition 1, 2, 3 further, we are going to end up with a total modulity of less than 1, which is not better than 1.85. So we'll stay with 1.85 and this community 1, 2, 3. Similarly for 4, 5, 6, if we were to partition 4, 5, 6, we're going to have 4 by itself in one community and 5 and 6 as another community. And again for 5, 6, the moduli score is going to be less than 1 plus 0 is going to be less than 1, which is not greater than 1.85. So we'll stay with 4, 5, 6 as one community with a modulity of 1.85. So this is then the final partitioning of the graph into two communities with a total moduli score of 3.7. Okay. Now we'll use another example. Okay, so this is a graph, so you can feed in the adjacency list for this graph and get the eigenvalues and eigenvectors. So this is the principal eigenvalue, the largest eigenvalue, and the corresponding eigenvector, and we know that all entries are going to be positive because this is a graph with all the entries going to be zeros or ones in the adjacency matrix. So the principal eigenvector indicates all vertices are in one community. Okay, and again we know these are also the eigenvector centrality values. Okay, so now we'll go to the second largest eigenvalue, which is 2.1175, and its corresponding eigenvector. Now we see here entries 0, 3, 4, 5 are negative, the others are positive. So that means you can partition this graph into 0, 3, 4, 5 as one community and 1, 2, 6, 7, 8, 9 as another community. And let's go ahead and find the modality scores for these two communities. For 0, 3, 4, 5, these are the possible pairs: 0, 3, 0, 4, 0, 5, 3, 4, 3, 5, and 4, 5. And these are the pairwise modality scores. So the total modality score for 0, again, you find the pairwise modality scores based on the entire graph. So always we will feed in the entire graph to our pairwise modality scores program, run that jar file and get the pairwise modality scores and use them in wherever the calculations you needed. Okay. Okay, so let me show actually the pairwise modality computation so that there's no confusion. So here we have 0 with 3, so 0 with 1, 0 with 3, 0 with 4, 0 with 5, and 1 with 2, 1 with 3, 1 with 5, 1 with 7, 1 with 8, then 2 with 8, 3 with 5, and 4 with 5, 4 with 6, 5 with 6, 5 with 7, 6 with 7, 6 with 9, 7 with 8, 7 with 9, 8 with 9. So these are all the edges. So let me save this. So I'm going to run the pairwise modality program. Okay, so these are all the pairwise modality scores. So you take for whatever the pair you need the scores from this result. Okay, for 0.3 0.7, for 0.5 to 0.4 and so on. Okay. Alright, so we get the total modality score to be for this 0, 3, 4, 5 is 2.67, for 1, 2, 6, 7, 8, 9 is 3.13. So that means if you had to partition this entire graph into two communities, you're going to get 2.67 and 3.13, which will add up to 5.8. So that is the modality score so far, 5.8. Okay. Now what we'll do is we need to decide whether to partition 0, 3, 4, 5 further down. Similarly, whether we need to partition 1, 2, 6, 7, 8, 9 further down. So in order to decide that, we need to use the next largest eigenvalue, which is 1.673, and the corresponding eigenvector. So we have here 0, 3, 4, 5 as one partition. That means we have to look for entries 0, 3, 4 and 5. So we see here 0 and 3 are positive, 4 and 5 are negative. So if we were to partition 0, 3, 4, 5 further as separate communities, we need to put 0 and 3 together in one community and 4 and 5 together in one community. The modality score for 0, 3 is 0.7, the modality score for 4, 5 is 0.55, so the sum is 1.25, which is less than what we have for 0, 3, 4, 5 together, which is 2.67. So we better stay together as 0, 3, 4, 5. Now what about 1, 2, 7, 6, 7, 8, 9? So if you look at the entries here, 1, 2 and 8 are positive, so they should be partitioned as separate community. Then 6, 7 and 9 are negative, so they should be partitioned as separate communities. Now the modality score for 1, 2, 8, these are the pairs and the total is 1.9. For 6, 7, 9, these are the pairs and it's 1.83. So 1.9 plus 1.83 is 3.73, which is greater than 3.13. So that means it's better to really partition 1, 2, 6, 7, 8, 9 as 1, 2, 8 and 6, 7, 9 as two separate communities. So eventually then we're going to save 0, 3, 4, 5 and then 1, 2, 8 and 6, 7, 9 as a community. So you have a total of 3 communities. And the total modality score is the modality scores of the individual communities. For 0, 3, 4, 5 is 2.67. For 1, 2, 8 is 1.9, for 6, 7, 9 is 1.83. So the sum of these 3 modality scores is 6.4. That's the total modulated score of the partitioning based on this eigenvalues and eigenvector based approach. Okay, so let's stop this video with this.